All right. So today we have Saghar Hosseini telling us about BF theory in symmetry TFTs. Take it away.
Okay, thank you. So I will today talk about the BF theories and how they can be obtained from a string theory. This is work done together. So it's based on previous work done together with Fabio, Federico, Sakura, and my advisor Iñaki, and also work to appear with Iñaki. So we know that in order to specify a quantum field theory, it is not enough to just know its local operators and their correlation functions, but also we need to know what extended operators are in the theory and what symmetries these extended objects have. And actually, there are quantum field theories which have the same local structure, yet different global structures. And this is because of direct quantization condition. So these extended objects, they can be electrically or magnetically charged or dionically, and then we cannot realize all of them in a given theory at the same time. So for example, we know that in 4D IMS theory, we can have line operators, charge operators, which are Wilson lines, Hooft lines, or Dionic lines, and depending on which ones you have in your theory, you have different global structures. So for example, here you have just electrically charged Wilson lines, and this theory has electric one-form symmetry, or you can have magnetic symmetries or Dionic symmetries, but not all of them, exactly because of this direct charge quantization, which is discussed here. Okay, now this is important because theories which have different global symmetries, they have different partition functions, and you can write the partition function as a sum, where the factors in the sum are determined by which bundles you sum over in the path integral. So these choices can be seen from the so-called BF theory, and the goal of this talk is to tell you what this BF theory is and how we can get it by dimensional reduction from a string theory. So I will first introduce the BF theory, and then I will talk about how we can see the so-called symmetry TFT from string theory, which I will introduce in a second. And I will go in the last part to derive the actual BF theory from a string theory. Okay, so the symmetry TFT is a D plus one dimensional topological field theory, and it encodes information about BF theory, which tells us about these choices of global structures. The higher structures, these include higher form symmetries, higher group symmetries, or more general categorical symmetries. And it also tells us about what possible anomalies our theories can realize. So in this picture, we have a quantum field theory which lives on the boundary of this D plus one dimensional symmetry TFT. And when we choose boundary conditions, we are fixing what global structure we have, and then what we obtain from the symmetry TFT is the corresponding anomalies for those symmetries for this fixed field theory now. Okay, now if we don't have any anomalies, then instead of a gapped interface which you had before, we have a gapped boundary, and fixing boundary condition just gives us the field theory with the symmetries. Okay, and so what is this BF theory? So for example, in the 4D IMS theory, which we had this different Wilson lines and Hooft lines, there we had the electric symmetry or magnetic and so on. We can write the BF action, which is defined in one dimension higher, as B wedge F, where B is a background field for the one-form symmetry, electric one-form symmetry, and A2 would be the background for the magnetic one-form symmetry. And so this is a non-invertible field theory, and depending on the boundary conditions that we choose, we can have different global structures. So if we were to choose Dirichlet boundary condition for A2, then we get two lines, and these B2 become the generators of the magnetic symmetry. And similarly, we could have different choices where we choose Dirichlet boundary condition for B2, and then in that case we have electric symmetries. Now, more generally,
so one question, Sophie.
Yes.
So why is the theory on top that boundary relative?
Yes. So this is a relative field theory, and once we fix which one of these boundary conditions we have, it becomes an absolute theory in the sense that it doesn't have different possible global structures, that is only defined relative to this bulk theory.
Okay, thanks.
Okay. And as we will see, these choices can be understood as choosing a Lagrangian subspace or a gauge theory, gauge group in our gauge theory. Okay, so more generally, you could have a theory in D dimensions with a BF theory in D+1, where you have a Q from electric symmetry and a dual magnetic D minus Q minus 2 from symmetry. And there the action would be given in terms of these background fields for these symmetries. And this is a discrete gauge theory. So now, again, this is a non-invertible theory, and we can choose boundary conditions to reproduce the choices of global structure for our theory. Okay, so how can we find this symmetry TFT from a string theory? So this is we do this by geometrically engineering our field theories from string theory or M theory. So in M theory, so if we start say with M theory and we put it on a product manifold like this, here we have a part which is the internal manifold, and the other part is where our field theory lives. So we know that there are branes in M theory. When wrapping branes around different cycles gives us different objects. So if we wrap branes on the cycles that live in the bulk, so this is the internal manifold. I just resolve the singularity, and when I wrap branes around the cycles that are in this bulk of this geometry, I get dynamical operators. And when I wrap branes on cycles which are defined relative to the boundary, so these are cycles that if you identify all the points in the boundary, you get a cycle, and it's an element of this group. So when I wrap branes on these, what I find are defects in the theory, and defects can be screened by the dynamical operator. So what we have to do is look at all the possible defects in the theory given by these cycles, and then quotient by the dynamical objects. Then we find the defect group, and this is actually not the higher from symmetry group. It is bigger because exactly we have these choices, and we have to choose a subset of this group. Okay, so how do we actually get a symmetry TFT? So what we do is we start again with this 11-dimensional theory, and we can get rid of the singularity as to whichever way we like, by deformation or resolving it, and then we get this, and then what we do, we integrate over this boundary to find a one-dimensional object, and this gives us a theory in one dimension higher than where our field theory is, an 8-dimensional theory. This is exactly where our symmetry TFT lives. Okay, so also we saw before that choosing these boundary conditions gave us different symmetries, and we had these. So when we chose Dirichlet boundary condition for A2, we got two lines, and then the B2 gave us the generators of the symmetry. So from the geometry, we can see that when we have of branes wrapping cycles which are defined relative to the boundary, then these will become the ones that give us the defects. And then when branes wrap cycles that are just defined on the boundary, these will give us the operators that generate the symmetry. Okay, so how do we actually get these this BF theory? So one way to see that there is this, so there are these different choices of symmetries is starting from, say, M theory. And when we reduce the fields into M theory, so in M theory we have fields G4 and G7, we can reduce this on this manifold, then they'll have a part that is valued in the internal manifold T2 and parts which are living in M7. Then these, reducing these fields, we get, from these we can get operators that are in the theory, that live in our field theory. So we know from these papers that these M theory fluxes, they don't commute with each other. And this in turn means that when we reduce the fluxes that these operators that we have in our theory, they don't commute with each other. And well, this is to the only true if we have cycles in our geometry which are interesting and link each other. If you have interesting enough topology, this happens. And so the fact that these operators do not commute means that we cannot realize all the symmetries in the theory at the same time. So what we have to do is to pick a maximal commuting set of these fluxes. And different choices of these fluxes give us different choices of global symmetries. So going back to the example of for the Yang mystery, we had well, if we find a defect group, is Z2 plus Z2, and picking a maximal set of commuting fluxes correspond to choosing a Lagrangian subgroup of this defect group. And this is given by, so here we have three choices. We can take the first, second factor, or the diagonal Z2, and we reproduce the three choices that we saw before. Okay, so how do we actually get this BF theory from a string theory? Okay, so before going into that, I should introduce some mathematical technologies. So usually we take our fields to be just elements to be differential forms. However, if we have topology, interesting topology in our internal manifold, for example, if we have a claim bottle, then there are cycles which are torsional. So here we have one cycle that is torsional. So if you go around this claim bottle, you have to go back to the same point. You have to go around twice. So this means that there's a Z2 torsional cycle here. And what we have to do to take into account this kind of topology is to promote our fields to be valued in differential cohomology. So they would have three parts. There is the curvature part, and which is just a form, and then there is a holonomy part of this cycle, and there is another part which tells us about this torsional component, and it's a two co-cycle with integer coefficients, and these three, and then the differential of this cycle would be that it's not so trivial. So these three, when you take the change in holonomy, you find that it is given by this relation. So this is not just a direct product, in other words. And then you can define your differential cohomology group as these cycles like modeled by exact cycles, which are boundaries.
So,
Okay.
so Sophie,
Yes.
so I didn't understand very well. So the three pieces,
Mhm.
so the first part is the field strength.
Mhm.
Sorry, I don't have the video. Let me put it. Wait,
So-
I don't know. Yeah. Okay, so the first part is the field strength. The second part, I mean, why is it? I didn't get very well what.
This is the
happened.
holonomy of the cycle. So it is valid. It's a one co-cycle with real coefficients, and so one way to think about it is to define it in terms of well, since these three parts are related, you could define it, the change in it, as the integral of the curvature. No, yeah.
Okay, and the third part, why is it a two co-cycle?
This is the topological part. So what we call just a second. This is called characteristic class of the of A. So when we, if this would give us the singular cohomology part of A. So if we have
I don't know
cycles, they would take value in this. So if you're not familiar with, yeah, so I don't know. So I mean, if we were to take cycles modeled by DC2, then that would define singular cohomology where, so if you say you take the torus and then study singular cohomology of it, then the first, it would have two one. I don't know if this is maybe I have to write something, but it would have 2 1 cycles, and then the torus itself would be a 2 cycle, and these are the cohomology classes of the torus. And
okay,
yeah, and if you have torsion, you have to look at that part, the singular cohomology part.
okay.
Sorry, I'm not sure if that's satisfying.
Okay, thanks. Yeah.
Okay.
Sorry, can I ask another question? What is delta here? So D is the Xera differential and delta?
So delta is the co-boundary map in it would be co-boundary map of these chains in, yeah.
I see. Thanks.
Okay, so we were saying, how do we get this BF theory directly by dimensional reduction? And we saw that these M-theory fluxes, when we reduce them, we get the symmetry generators, or we get some operators. And for example, in the 7D case, we had G4 and G7, and when we reduced, we got the two fields B2 and C5. And B2 is the background for the one-form symmetry, and C5 is the background for the four-form symmetry. So also we saw that earlier, that these fluxes G4 and G7 didn't commute, and that meant that we had to pick which one of these operators we can realize in the theory. So if we were to get this BF theory, the BF action from a string theory by some reduction of some action in a string theory, then maybe it could be that it's from the reduction of the kinetic action of M theory, because there you have G4 and then you have a star of G4, and you know that G4 and G7 are dual, so it looks like if you reduce this, maybe you get the BF action, but that actually doesn't work. So what you have to do really is to construct a self-dual action properly for these fields for G4 and G7. And to see how to do this, let's consider the example of the Carl scalar in 2 dimensions. So there, there we have a self-dual Carrel scalar, which is self-dual. Yeah, and then the action naively would write as d phi wedge star of d phi, but we know that this is not a very well-defined action and it doesn't encode the self-duality constraint. So what we can do is define a Chern-Simons action for it by coupling it to some background field A. And so we can do this by writing the action this way. Now, if you do a Gauge transformation, the action changes. It has a the variation is non-trivial, and we see that this is exactly the boundary term you would get if you were to write down a Chern-Simons edge dA under the change of A being d lambda some 0 form. And so because of this, we can define this action for this self-dual field to be this Chern-Simons action. And if A is not globally well defined, then we would be in trouble because we cannot just write A. So what people usually do, they go into one dimension higher and write the action as F wedge F. But that is not necessary if you have these fields to be valued in differential cohomology, then you can just write it in 3 dimensions and promote these A's to be differential cohomology classes and write it as A dot A. Okay, so to see how this action actually encodes the self-duality constraint, what we can do is add to this action a term which is A wedge star A, and require that this A vanishes at the boundary. Then from the variation, we see that we automatically get this self-duality constraint. And also to see how we actually get this action actually gives us the action for the self-dual field. What we can do is decompose our field A and D into time and space components. Then we require that this the symmetry of the theory given by the gauge transformation must be invariant under at the boundary with regards to time, and that is imposing that A naught vanishes at the boundary. So doing this and then substitute these expansions into our Chern-Simons action, we see that we get this term, and here A naught is a Lagrangian multiplier, so we have this condition. So what we see is that under the variation, dA bar is 0. In other words, A must be the variation of dA must vanish at the boundary. So this means that if this means that we can write A as d phi if A is topologically trivial, we can write it as d phi, and then we can substitute back this into this term, and we get back this action that we had originally for phi. So what is happening here really is that we have these gauge modes in the bulk that become the dynamical fields on the boundary when you impose the boundary condition. Okay, so similarly in M theory, we can do something similar. So here we have fields G4 and G7, and G4 is not self-dual, but so nor is G7, but the pair G4 and G7 together, they form a self-dual field. And And we can similarly couple this field G to some background B and define a Chern-Simons action for it. So here we would have, we would go also to 1 dimension higher. So enter is 11 dimensional, and then this would be a 12 dimensional Chern-Simons for the field G. So here, once we reduce this, we find that the action B is B8 dot B7, sorry, B5. And now if we consider, for example, the reduction that we had before for the 7 dimensional theory, now we would take this N12 to be some the boundary times some W9 such that this W9 has boundary where our symmetry TFT lived or our BF theory is defined on. And substituting in the expansions for this B8 and B5, we get some linking pairing, which is integrating out this boundary that we had before in the picture. And the other term we find is nothing but this coupling between B5 and B2. In other words, the BF theory. So here we have a 1 from electric symmetry and a 4 from magnetic symmetry, and we reproduce the BF term in this manner. Okay, sorry, my talk was very, very short. I didn't realize it's gonna be this fast. So we see that we can get the BF action from the Chern-Simons term action for the self-dual field in a string theory, and to see this, we have to look at we have to promote our fields to be valid in differential cohomology, so that we include torsion. So the BF theory, it can be useful to study non-invertible symmetries. So there were some papers, for example, this one, where they needed to use the BF theory, or the later papers, these theory papers. They also had to introduce this BF theory in their construction to get the non-invertible symmetries, and they had to use this non-commutativity argument, but this way we could actually drive it exactly to use. Also, what we can do is try to find a BF theory of so many different theories that can be constructed for from a string theory. Finally, we can explore a lot of consequences that these different choices have for our theory. Here are some of the examples, including RG flow. So you know that these symmetries must be preserved. They're topological, so they're preserved along RG flow. So we could use that to study what theories are connected, are like dual to each other in that sense. We can also learn about dualities like electromagnetic duality. So we know this in our, say, for the example, we had these different choices, SO3 group or SU2 when we know these are related by SL2Z transformation. So we can, in that sense, study dualities. And okay, so since I have time, I have an extra slide. Let's go through it. So we can also derive the anomalies using this method. So if we were to study with M theory topological action, which has this form, it has G4, C3, and then we promote it into be valued in differential cohomology. It takes G4, becomes G4, and there are these other terms. And if we reduce our fields again, in this, we substitute for G4 and G in here, then we can write G4 as B2, T2, which we had before, and also there is another component. And when we reduce it, we'll see that we can integrate over the fields that are valued on the boundary, and we are left with some anomaly polynomial, which tells us about the anomalies that we have between different symmetries. So here we have a one-form symmetry and a two-form inner-Stampman symmetry. Also, I should say that this is not restricted just to M theory. We could also do exactly the same thing in type 2b, and there we have a F5 for 5-form flux, and we can construct an action, a Chern-Simons action for that reduce it to get, for example, BF action for 4-dimensional theories or 6-dimensional theories that we find from a string theory. Okay, okay, sorry for being so short, but yeah, that's it. Thank you.
All right, let's thank Saghar. And do we have questions?
So I have a question.
Yes.
I actually arrived a few minutes late, so maybe I missed this, but in the BF theories you construct from M theory on M7 times C2 mod Zn. So the BF theory is the symmetry TFT, but it's the symmetry TFT for what 6D theory?
So which one? This one?
So you could even go back earlier. So I'm talking about the construction from M theory, where you have M7 times C2 mod Zn. And then you derive the BF theory from this M theory perspective. Yeah, this one here, exactly. Mm-hmm. So the BF theory is supposed to be the symmetry TFT for some 6D theory.
Yes, so this is part of the symmetry TFT. There could be anomalies, other terms in the symmetry TFT.
Okay, so there are a lot of 6D theories. So I guess my question is, which one are you capturing the BF theory that gives you the symmetry TFT by doing this procedure here? Or so, is all of them? Well, I doubt it's all of them.
There are a lot of what, sorry?
There are a lot of 6D theories.
6D theories.
Which, for example, you can construct as, you know, living on a domain wall inside of M7 in this kind of M theory construction.
So here the field theory is 7-dimensional, and then BF theory is 8-dimensional. So
okay, but then it's not a super conformal theory.
It has n equal to 1 SUSY. It's not.
But not conformal, I guess, yeah. In 7D. Mm-hmm. Okay, I see. So it's really about 7D.
It's super Yang-Mills with the SUN Lie algebra.
Okay, I see. Very good. Okay, perfect. Thank you. That clears that up.
Okay, more questions. Okay, so I guess in that case, let's go over to the informal part. But before that, thank Saghar one more time. Stop the recording.